Okay, in this video, we will give an introduction to Simulink. And for the introduction, what I'm going to do is I'm going to use this book called Introduction to Simulink with the Engineering Application by Stephen Carris. Okay, so this is the book, and it has some interesting contents, but I'm going to consider only some of the essential parts from this book for our course. Okay, so this is the book which I'm going to use. Let me put this book aside, and I have prepared two slides from this book. Okay, so in order to solve some examples in this book. Okay, let's say how we can make use of this Simulink in order to solve some engineering problems. For that, let's consider an engineering problem which is solving an LCR circuit. So this is an LCR circuit. Right. So this is a LCR circuit, right? Okay. So because we have resistor, inductor, and a capacitor. Okay, and here we have the voltage source, and the voltage source is given like this, which means it's a unit step input. It's like until t is equal to 0, we switched it off, and when t is equal to just 0 or 0 and above, we switch it on, so that the voltage up to 0, it was 0 voltage, and then from 0 onwards, it's been 1 voltage. That's what the step input. Okay, so we are giving the step input over here. Okay, as a voltage source, and then we have the resistor with this as the resistance, inductor, yeah, the inductor with this is the value for the inductance, and the capacitor with this as the capacitance. Okay, and we call VC as the voltage across the capacitor. Okay, now we have this circuit, but what is the mathematical representation of this circuit? Okay, so now so if you see, we have the current, okay, which we call as I, and it could vary with respect to time. So it's I is a function of time. Okay, so now we know that I is the one which is passing through resistor, inductor, and also the capacitor with the same quantity. Okay, so since there is no branch, so whatever the current passing through resistor, the same current will pass through the inductor as well as the capacitor. Okay, now if that's the case, I can be equal to C dVc by dt. Okay, so that's the relation between the voltage across the capacitor and the current which is passing through the capacitor. Okay, and C is the capacitance, this value 4 by 3. Okay, and now from the Kirchhoff's voltage law, what we can do is whatever the gain in the voltage through the source has to be equal to the drop in the voltage across each electrical element, and it will completely drop in this loop. That's what the Kirchhoff's voltage law. And from that, the voltage drop across the resistor is Ri, okay, and the voltage across the inductor is L di by dt. Okay, and the voltage drop across the capacitor is Vc, and that is equal to the source voltage, which is Vs, but we know what is Vs, which is U naught. Okay, fine. Now let's make use of this equation. Okay, if I make use of this equation, I will get Rc dVc by dt plus Lc d square Vc by dt square plus Vc equal to U naught. Okay, and if I substitute the value for R, C, L, everything, then finally I will get the following equation, which is and I substitute and then I rearrange a few factors so that I will get d square Vc by dt square plus 4 dVc by dt plus 3 Vc is equal to 3 U naught. Okay, but what's U naught? U naught is equal to 1 for t greater than 0. Okay, so which means we can say which is equal to 3 for t greater than 0. So that's the differential equation. Okay, so this is the differential equation we have. Right, this is the differential equation we have, and if we solve this differential equation, we will get the voltage as a function of time. But wait, we have a problem. This is a second order differential equation, but we require some initial condition, right? So in the problem, the initial conditions are given as follows. Okay, so let me write it here. So I at 0, the current initially is 0. Okay, so when t is equal to 0 or before that, there is no flow of current. Okay, there's a flow of current only after I close the circuit. And the another thing is Vc, okay, of 0, which is equal to 0.5 volt. Okay, so we also know what's I, which is C dVc by dt, and that's 0, which means dVc by dt is 0. Okay, so those are the two initial conditions. So these initial conditions plus this differential equation together is going to give a solution Vc as a function of time. Okay, how to solve that, I believe you know from your differential equation class. Okay, so I'm gonna skip that part, but you can revise your differential equation lecture notes, and then you could solve this problem. But we are not going to repeat that, but instead what we are going to do is we are going to see how to solve this problem using simulink. Okay, so still I haven't shown you what's a simulink, but I will show you in a few minutes. But what we are going to do in simulink is we are going to construct such a circuit, okay, and then we will solve for Vc. But how this is relevant But because, I mean, this is actually representing the differential equation, but it doesn't look like that, right? But let me explain why it represents the differential equation. So what's the differential equation? Let me rewrite the differential equation for your reference, which is, let me write it over here. So d square vc by dt square plus 4 dvc by dt plus 3 vc is equal to 3 when t is greater than 0, right? Okay. And we have initial conditions as well, which is vc of 0 is equal to 0.5 volt and dvc by dt is equal to 0. Okay, so these are the two initial conditions. Now let's see how this circuit represents the differential equation. Maybe I'll do one thing, I will change the color. Okay, I think that would be better. Okay, so now let's see. So this point actually contains the signal of u naught. Okay, and here what do we have? We have, so we know that u naught is equal to sorry, not 0, 1 for t greater than 0. Okay, and here we will have, so it's like a multiplier. So whatever the signal comes here, it will multiply by this number and it will give that as an output, which means here what we will get? We will get, so if this is 1 and this is 3, 3 is what we will get. Okay, and this is summation. Okay, so here whatever the signal comes in, it will take all the signal, sum it and give it here. Okay, so let's see what are the signals which are coming. So first let's check here. So here it represents vc and here it is being multiplied by -3. So what I'm getting here is -3 vc. Okay, and similarly here I'm getting dvc by dt, which means it's getting multiplied by -4. So here I'm getting -4 dvc by dt. Okay, and now I'm getting sum of all these three things, which means uh, -4 dvc by dt -3 vc plus 3, and that is equal to d square vc by dt square. So that's how we actually got this equation, right? So we have got this equation. But wait, how do I get this vc and dvc by dt, right? So we can get dvc by dt if I integrate the signal whatever comes out of this one once. Okay, if I integrate this signal once, then I will get dvc by dt, because here it's d square vc by dt square. I'm integrating once, so I'm getting dvc by dt. Okay, and if I integrate one more time, I will get just vc. Okay, so therefore I use these integrators in order to get this dvc by dt and vc. Okay, but what about the initial conditions? These two initial conditions, those initial conditions I will define while I'm using this integrators. Okay, that I will show when I do the circuit in simulink. Okay, so now you have the understanding of the meaning of this circuit, or the relation between this circuit and the differential equation, right? Okay, now let's make the circuit, and then we'll solve and we'll see the answer, whether we are getting the right answer. Okay. Okay, so for that, let's go to MATLAB. So once you open MATLAB, this is the window you will see. Maybe in addition to this, you may have an editor, but that's okay. So more or less, this is what you will see. But in order to run Simulink, just look at this one. Okay, so this is the Simulink button, and if you click on that, you will get a new window like this. And let me, yeah, you will get a new window like this. And let's choose a blank model. Click on the blank model, and let's start creating a model. Okay, so let me maximize it, and this is the space where I'm going to drag and put all the blocks, and then connect the circuits. Okay, between give the connection between the blocks. Okay, and then I will put some probes in order to measure uh, the voltage or the results. Okay, so let me refer the book, how the circuit is going to be. Okay, so from the book, if you see, finally this is how you're going to get. Okay, so step, and whatever you're going to multiply, it's been called gain. Okay, the adder, integrator, and the scope is something that you want to see the result. Okay, so what do you want to see? You want to see the voltage, right? So if you want to see the voltage, then you connect that voltage to the scope so that you could read the voltage. Okay, okay, so this is what we are going to construct. Okay, so let's see how to construct it. The first thing is, okay, we have to, if you go to this library browser, okay, so you will get all the necessary blocks, and the first thing is you need step. Okay, so if you type there, and you will get so here you have it. So all you can do is drag and put it there. Okay, and then we have something called gain. Is this being opened? Yeah. Okay, now let me gather gain, and that's our gain. Okay, and we have gain, and then I actually need two more gains, so let me copy and paste, so I get one more, and then one more I need. Okay, so I have got all the necessary gains. Okay, and we have the default value 1. Later we'll see how to change. Okay, now what else we need? We need integrator. Okay, so we'll search for integrator. Right, so we have the integrator. And how many integrators we need? We need two integrators, so let me have two integrators. Okay, and what else we need? We need to sum all the signals, we need adder. Okay, so this is the adder. Let me gather that one as well. And then I need scope in order to see the results, right? So this is the scope. Okay. Now we have all the blocks. Now we need to connect everything. Okay. So let's start connecting it. Mm, okay. So just if you go there, your cursor will change its symbol, and then once you reach there, you got that change in the cursor symbol, then click on it and then connect to whatever you want to connect. Okay, that's it. You got the signal. Sorry, you got the circuit. Or you wired it. Okay, and what you have to do, you have to connect that one to the adder. But if you see, the adder has only two things to add and one thing to give as an out, right? So if you want to increase it, just double click on that. You will see the list of signs, and it has two plus, and if you add one more plus and say either apply or okay, yeah, you will get the three inputs and one output. Okay, and maybe, oops, okay, I'll delete that part. I just want to expand it so that it looks neat. Okay. Now what I'm going to do, the circuit, I have to give this one to an integrator and give this one to another integrator. Okay. And this one I will connect it to the scope. Okay. But so here I have 3 u naught, and here d square v by vc by dt square, and once I integrate dvc by dt, and once one more time if I integrate I will get vc. Okay, but this one I have to whatever the signal I'm getting, which is as vc, I have to gain it and put it over here, right? So how to do that? I can do it by changing the gain value. Okay, but even before I change the gain value, I would like to do one more thing. I want to flip it, okay, so that the arrow will focus on the other side. Okay, how to do that? Let me, is this how I do? No, let me right click it, and I will have this format, and in the format let me just flip the block. Okay, if I flip it, yeah, so my arrow mark has got changed. So let me flip this one as well. Okay, now what am I going to do? I'm going to connect it. Okay, okay, I'll drag it over here. And similarly, let me notice still I haven't given the appropriate gain. Okay, so now what's the gain I have to give here? The gain is 3. Okay, so see, I just double clicked it and there's something called gain, and there I need to change it to 3. Okay, okay, and here I have to give the gain of -4, so -4, that's it. And here I need to give the gain of -3, -3. Okay, So the circuit is over, but I haven't given the initial condition. Okay, so here to give the initial condition, so two initial conditions. One is rate of change of voltage and then voltage when t is equal to 0, right? So to give the rate of change of voltage, I double click on that, and here if you see something called initial condition, and here the default value is 0, and that's the value I want to give, so I leave it as it is. Okay, and then I click on this one, double click on this one, and here the default initial condition is 0, but what I need is 0.5. Okay, I give that and I say okay. Now that has been updated. So the entire circuit has got completed. Now what I should do, see this button, run, I need to click on that. So once I click on that, it ran and it has got completed. It's ready for the next action. Okay, and now I want to see the result. So for that we have the scope. Okay, so if you click on the scope, double click on the scope. Okay, so what do we have? So it's like you know, this step input, it happened, the input happened when t is equal to 1. Okay, for our analysis, whatever the t is equal to 0 is what t is equal to 1 in this step input. Okay, so initially the voltage is 0.5 and I didn't close the circuit, and the voltage across the capacitor is being dropped. But once I close the circuit at t is equal to 1, then what's happening? It starts increasing and then it kind of getting saturated to the value which is Vc is equal to 1. Okay, so this is the answer we will get even if we solve this differential equation analytically. Okay, the same thing we have got using our simulink. Okay, fine. So what we shall do is we will see how to solve the differential equation once again using simulink, but different in a different manner. Okay, so right, so you just practice this method, and you also practice some other differential equations and then check for yourself. Okay, so in the next video we'll see the next approach. Thank you.